But let's start now with the talk of Hendrik Weber. May I ask you to the podium? So, he got his PhD from the University of Bonn. Bonn is actually, of all the speakers today, some place that plays a role, like the University of Warwick, where you went to do a postdoc, I think, with Erhard and Hairer, and then you became a professor there from Warwick. Hendrik then moved to the University of Bath, and very recently he moved to the University of Münster, where he's a professor for applied mathematics. And you can see the title of his talk here, so please.
Excellent. So thanks a lot for the invitation. It's really a pleasure to be here at this occasion. So, I mean, for this workshop in honor of Martin, it's really great to be here. So I chose the topic for today. I think it's a nice topic because it's sort of, one could also call it sort of Martin's theory at work, because even though we have written the paper, I would say 85% of the tools have been invented by Martin, and I will use this as a good excuse to explain some of the ideas that he has developed. Also, I mean, he hasn't only provided the tools, he has also provided me with one of the co-authors who was his PhD student in Warwick years ago. So yeah, Konstantin, who is now recently moved to Michigan, and is also joined with Paolo Grazieschi, who is my finishing PhD student still in Bath. Okay, so I start with a sort of philosophy slide, which is, so if we're interested in understanding the large-scale behavior of some microscopic models, interacting particle systems, then very typically they're often, I mean, in many situations, they're described by a nonlinear SPDE. And this is the so-called hydrodynamic limit. And again, this is a classical topic that many people have worked on. And just as an example that people may be familiar with, you can look in the, I've looked it up in this classical book by Kipnis and Landem, is that if you look at the zero range process, which is an interacting particle system, and if you look at it at the right scale, then the effective behavior is described by the Peirce medium equation. And then what people go is to next order when you're interested in the fluctuations around this deterministic behavior. Then very often you see a linear stochastic PDE. And so this is often given by the linearization, the linearization of this hydrodynamic limit. And this is the kind of, if you want, this is the law of large numbers, and this is the Gaussian CAT. But then sort of this, the topic of this talk, there are some special situations, specifically near the onset of instabilities, when there's an instability for this hydrodynamic limit equation, where one can see some nonlinear SPDEs, or you can see some non-Gaussian fluctuations. And I mean, this is really where, yeah, the theory of regularity structures becomes useful in understanding these objects. And I will talk about this in a minute. Well, this is the content of this talk. And I start this by recalling a very classical example, which is the convergence of the, if you want, the weakly asymmetric simple exclusion process in the KPZ equation. So here one starts with looking at this surface model. So one should think of this red line here as a surface that moves upwards, separating, say, whatever, water down here and ice up here. And so this is a discrete model. So you should think of, I've linked them by these lines, but you should think of their function from Z to Z, and they can always go up and down only by one. And then the way these dynamics work in this model is that if you have such a corner down here, then a particle can rain down from the sky and be deposited here. And the opposite can also happen. So if you have a corner which goes upward, then the solution may go up and go back into the sky. And that this can happen at all these downward corners. So something can rain in here, and these upward corners can go away. And sort of what makes this grow upward is that this deposit happens slightly more frequently than the going away. So you have this parameter epsilon here, which tells you how much more you like to go up than you like to go down. Okay. So a relatively simple model for surfaces. And so now this is, if you want here, this leading order, if you want hydrodynamic limit, is pretty simple. It's just, let's say we start in a flat enough configuration. It's just a straight line moves up at a speed. And the speed is exactly epsilon to a half, which is exactly that epsilon to a half. So it's just that. And then the interesting thing that Bertini and Giacomin found in their really very important paper now is that if you look at this field, you rescale it in the correct way. So you look at large time scales and you look at large spatial scales, and then you remove this linear speed that we had here. and then, well, tune it down at the correct scale, then you actually see that this is governed by the KPZ equation. And the KPZ equation is here this now nonlinear because of this term, stochastic partial differential relation. Psi for me is always going to be a Gaussian space-time white noise. And but I mean, there's that. I mean, so one thing that is to be noted, and I want to, this will come back later, is we have to make quite an effort to see this nonlinear term here. So we really have to look at a very special scaling. And the one thing I want to really stress from the beginning is that we had this parameter epsilon here, which we used to look at this, used to parameterize the time-space scale at which we look at. But this was the same epsilon that also used to scale the asymmetry. So we have, it's not the situation where we have a single simple model and we look at its large scale behavior and it's given by something nice, but it's actually a more specific situation where we have to tune the model as we zoom out, and we have a parameter in the model and that we have to tune according to the scale at which we look at it. So this will be characteristic for what we will see also later. The other thing that, I mean, is kind of clear, I will come back to that also, is this need for renormalization. I mean, as was already mentioned in the introduction, I mean, these are pretty irregular objects and one has to make an effort to make sense of this, and I will come back to this in a minute. Okay, so that's, yeah, that's sort of the classical result. And I want to now present a different model where very similar thing can be observed. And this is actually, I'm going to follow here for the next couple of slides. I will explain a calculation that I haven't invented myself. So this is actually due to a really beautiful survey article written by Giacomin-Lebowitz-Presutti in the late 90s. And sort of the concluding thing of the next couple of slides, I'm going to really walk you through the calculation, is going to be there should be a nonlinear SPDE, but in the 90s there were no tools available to actually prove that. Okay, and so let me do that a bit slowly. So we start with the Ising model. I presume most of you will be familiar with the Ising model, but let me just walk you through it quickly. So you have a configuration of plus or minus spins. So the red here, say, is plus, and the blue dots mean that at this position the spin is negative, say. And then to each such spin configuration we associate the Hamiltonian, which just counts how many spins are aligned or anti-aligned, and we have this parameter kappa here that kind of sees how much the spin I cares about the spin j. We're always going to look at ferromagnetic models, so kappa is going to be non-negative. And then we associate to this Hamiltonian this Gibbs measure with this temperature parameter beta. And the specific situation that we're going to look at is the case of Katz interaction, which means that this kappa parameter here, kappa ij, is going to, well, has a parameter gamma, and it has this form. So this curly kappa, you should think of a smooth indicator function of a ball if you want. And then we rescale it so that we see all the particles, the particle at the origin here sees all the particles at distance gamma inverse here. And I mean, the smaller gamma, the less it cares about individual spins. Okay, so this is so if you want, the spin at this side interacts with the average spin of this whole box, and the parameter gamma determines how big the box is that we care about. And again, I mean, many of you will be familiar with mean field model, where every spin corresponds to everything and the geometry is completely forgotten. That corresponds here to the case gamma going to 0. And if you want the normal Ising model, where things, where they interact with nearest neighbors, corresponds here to the case where gamma is equal to 1 if you want. And this parameter gamma is an interpolation between those two things. And then we look at this on the Glauber dynamic, heat bath dynamic on that. So this is pretty easy to define. Each of side has an independent Poisson clock, and when it rings at size I, then the spin flips or doesn't flip, and it flips with this probability. This is just given by the probability of the flipped side over with this normalization. So the higher kind of if we like to flip, if it's more favorable for the Gibbs measure to flip, then we do. If we, I mean, then it's more likely to flip. Okay, so this is dynamic, and it's relatively easy to see that this defines a reversible Markov process for this measure. And now, so we're interested in large-scale behavior of these fluctuations, and I already say that the parameter gamma here is going to play the same role as the weak asymmetry epsilon that I had in in the weakly asymmetric single exclusion process. So again, I mean, the observable that we will look at is here this locally averaged field, and it's convenient to use define the same kernel kappa that defines the interaction as for the observable. And then if we want to analyze it, the first thing that one always does is you decompose the evolution of this observable, which now depends on time and the location I. So this is the location around which we look at local averages. And then we always get sort of this decomposition into a martingale and if you want the drift term, the generator. And so in this case, I mean, that's sort of the beauty of this Katz model, that we actually have a very explicit closed form of this part for the generator. So this actually already satisfies a closed equation, which is very much not the case for typical hydrodynamic problems. So so in a sense, we have made our life much easier here. So it has this form H minus this local average of the kappa and then of this tanh. And now we develop the tanh because we would expect this H to be typically pretty small. And then you see you have here sort of this thing interacts with this. So think of beta close to 1. So then you have this here, which looks a little bit like a Laplacian. And then you have the correction. And then you have next order and Taylor expansion, you have this cube. Okay, so that's nice. And so now this suggests that something interesting may happen close to beta equal to 1 when this is really a Laplacian. And this is also in this kind of scaling that we have looked the critical temperature for the mean field model. So if we were in the situation where gamma were close to 0, the way we've set it up, this would be the value for which the behavior of the mean field model would also change. So that's perhaps interesting. And so now what we're going to do, just like for the weakly extrusion process, we're just going to rescale it, and we're going to figure out in a minute how we rescale it. So we look on large scales, large time scales, large spatial scales, and of course these delta, alpha, epsilon parameters are to be determined. And then, well, if you write it in the correct coordinates, what you see is this thing that now looks already much more like a stochastic PDE. This here is the martingale term, and I've chosen the parameter so that this looks like an approximation of space-time white noise. This looks like an approximation of a normal Laplacian. And okay, I mean, the other things just look like what they look. And so then, I mean, this suggests that we should choose these parameters to be all equal to 1. And so first of all, we want to choose beta close to 1, of course. But let's look at the other parameters first. And this is quite interesting. So now what you see, this fixes uniquely all the parameters in scale of fix of gamma. So this is again the situation that we had before for these weakly asymmetric exclusion process, where we kind of really had to zoom in exactly the right way in order to see something interesting. But perhaps also interesting to observe here is that you have this behavior. If you look at the exponent 4 minus d, 4 minus d, 4 minus d, so clearly D doesn't want to be 4. And you see this already here, okay? So this is fine, of course, in dimension 1 to 3, and in dimension 4, it doesn't work. And the other thing that I haven't spoken about is this beta. So the beta, this suggests, of course, that we should choose beta equal to 1, which would be this critical value for the mean field model. But we can, in principle, allow ourselves some correction here. So we could be able to allow some correction to still get an order 1 term here in this limiting equation. But the correction should be pretty small on the scale of this alpha. I mean, alpha is small. Everything is chosen in terms of this parameter, okay? So we could, in principle, allow some near critical temperature and still get this get a non-trivial term here in the equation, linear term in the equation. Okay, so this calculation, as I told you before, is completely taken from this classical paper by these 3 authors. And so they conjectured, well, in some way, I mean, they knew a bit about the limiting equation, but they conjectured that this should be, that you should be able to pass to the limit, gamma to 0, and you should get such a nonlinear stochastic PDE. Very much like we had with the KPZ equation, you would expect to see, again, nonlinear fluctuation in this very specific scaling. And so the problem was why this wasn't proved for many years after they did, because what does this even mean? And that's where Martin's work came in. So this SPDE here has another name in the literature. It's called the stochastic quantization equation. It has, I mean, one reason why one might suspect that this is hard to solve is sort of this observation that if you were able to just define this equation with space-time white noise, then at least formally you would immediately see that, I mean, it's not hard to see that this should give you a Markov process which is reversible with respect to this this thing which is called the Euclidean 5-4 quantum field theory. And this is a model that, I mean, has been around in mathematical physics for a really long long time. So the construction of this measure and verifying that it satisfies the correct axioms is indeed actually a very classical problem of mathematical physics. And it has been resolved now many years ago in the 70s, I mean, by many authors, but let me just mention these famous papers by Glim and Jaffe. But this is, I mean, hard, right? I mean, this was at the time was a big breakthrough, and it's really non-trivial. And I mean, the fact that it's hard is also these results, which are very recent. I mean, in particular here by Eisenman and Duminil-Copin, that if you look in dimension 4 or larger, then there is actually no non-trivial. There is actually no non-trivial 5⁴ theory, and in a sense, this 4 is the same 4 that we saw on the scaling on the previous slide. So the fact that this 5⁴ theory doesn't want to live in 4 dimensions is sort of the same reason why my exponents didn't want to work in 4 dimensions previously. So I mean, again, I mean, this measure had been constructed. So in principle, one could expect that this could also be done for this dynamics, which is like a nice Markovian dynamics for this measure. And actually, people tried this for a long time. So this had been around in principle. An approach through the dynamics. If you want some sort of Markov chain Monte Carlo, where you just run the Markov chain for long enough, and then get a sample from the measure, that had been essentially proposed in the literature already by Parisi and Wu in the early 80s. But sort of if you go kind of through history in the 90s, and so there were people who tried it, but they tried it in 2 dimension. Okay, so the 2-dimensional result was supposed to be hard, and 3 people didn't even dare to think about it, basically. So this was, I think, I'm aware of a single paper on the dynamic 543 equation from prior to Martin's work, and that essentially says that you can't, the Dirichlet form is not closable. That's so that's it. So people, I think, were not even daring to look at that. And sort of that is what then Martin did in his really breakthrough paper in this Inventiones paper on the theory of regularity structures. Well, by now almost 10 years ago. But yeah, and I want to actually, I mean, for this audience now, I know before I do that, I want to actually tell you a little bit more about this measure. And I want to talk about renormalization. And again, this is sort of the classical picture, the without dynamics, so that has been known. I mean, of course, this expression as such doesn't make sense in any way. So you would always have to basically view it, do discretization. You put yourself, say, on a finite domain, and then you discretize it with some lattice spacing epsilon. And then you write down, now here, this product measure over infinitely many Lebesgue points. This makes sense. And you take your favorite approximation of the Laplacian or of the gradient on the lattice, and you just take kind of this lattice scaling that has the correct Riemann factor here. So this is the kind of the natural way of approximating an object that should be this in the limit. And already sort of in the 70s or 60s, people knew that one has to actually do something a bit subtle in order to pass to the limit. So in order to get non-trivial limits, one needs to choose this parameter A, the mass parameter, which I've chosen with a wrong sign here, but it has to compensate the sign of that one. One has to choose this in a divergent way. So this has to diverge in 3 dimensions, like 1 over epsilon, epsilon being the lattice spacing, and then there's this logarithmic subdivergence that you still have to do. Okay, so this was known in the 70s, but nobody really had a clue what this is supposed to mean, what this was supposed to mean on the level of an SPDE. So it was clear that something similar should be done on the SPDE, but there was really no technique around how one would go about doing that. And sort of technically on the level of SPDEs, if you look at that, this the same problem presents itself as a regularity problem. So, I mean, the first, I think this was really already inside. I mean, everybody knew perhaps that this field here is going to be a distribution. Okay, I mean, that's fine. I mean, but Schwarz distributions, the space of Schwarz distributions is pretty big. So there's a lot of really irregular objects. And I think one of the, perhaps, I mean, by now kind of obvious that when one wants to actually quantify how irregular something is, and sort of now if one has the right way of doing that, then one can say, well, this object, this space-time-wide noise, is a noise of regularity in 3 dimensions minus 5/2 in the correct sense. Okay, and then now if the world is kind of good, then the heat operator should improve regularity by 2. So then this phi should be a solution of regularity, distribution of regularity minus 1/2, which I'm not going to explain what it means. So okay, and then we're back to the problem that we already knew, that we don't know how to cube distributions. Okay, so this was of course the problem that we had on in this construction of the measure, and now we have the problem here also on the level of the SPDE. And again, I mean, prior to Martin's work, there was no notion of a product, and there was really no technique to implement the necessary renormalization in on the level of the SPDE. It had been done on the level of the measure, but on the SPDE, really people didn't know. And I should also say, I'll come back to that in a little bit, that actually this problem is characteristic for a whole range of really interesting SPDEs. So the KPZ equation was already mentioned earlier in my talk and also in the introduction, but there's actually quite a few more. So this parabolic Anderson model, the quantization equation for Sine-Gordon. Now very recently, I mean, Martin has some work on the stochastic Young-Mills flow. So, I mean, there was really this whole class of really interesting equations that people, I mean, just didn't dare to even look at rigorously mathematically. It was completely considered out of reach. So, I mean, okay, for the KPZ equation, there's a workaround, but for the other ones, it's there was just really nothing. Nobody knew how to do anything. And I'm going to actually take now a few minutes to explain in a little bit more how this now works, how the solution that Martin did at the time then works. So we look again at this equation here, and sort of the first thing we want to do that was not his invention, that was done before, is to remove the worst term. So we got perhaps the invention is just this kind of slightly bulky notation. So we're going to call this thing pi of this. This is a tree with just one node. So this is sort of the worst term. If you think about it, I mean, okay, this term is going to be better than that. So we're just going to isolate this term and put it on the right-hand side of the heat equation and subtract it. And then the remainder is going to be better. So that is here, just plug it in, and here I expand that. So that's fine. And so now we have, again, these ugly products that we have to define, but that is okay because these are Gaussian fields and we know we have to renormalize them. We put some constants, but that's okay. We can sort of renormalize Gaussian fields, but we cannot renormalize solution to SPDEs because we don't know them. Whereas for explicit Gaussians, it's kind of easier. So that we can do, and that I now do by this different notation where I replace these by these more fancy trees, okay? Again, I mean, at this point, this was not his invention. This is sufficient to solve the 2-dimensional case, and this was done in a paper by Adaprato and Debuche already in 2002. So that was sort of known. And so now, how do we go further? So this doesn't work yet in 3 dimensions. So that kind of the resulting object V now in 3 dimensions is better than the original phi. So I mean, I haven't introduced this whole regularity power counting, but believe me, it's going to be of regularity just below 1/2. But that's still not enough because the things on the right-hand side are too bad. So we cannot, still not good enough. So let's go further. And okay, so I've already also put the next worst term on the left-hand side, but I don't want to talk about it. So I've also done that because now sort of the interesting problem where I mean, there were also people who had subtracted the second term, which is per se now not such a great invention. I mean, if it works once, you can do it again, so that's fine. But sort of the thing where previous attempts got stuck is this product here. So this you can't just put on the left-hand side because it multiplies the solution. And again, I haven't discussed the power counting, but this V will have regularity plus 1/2. This will have regularity -1, and sort of the power counting goes that the sum of regularities has to be positive in order to be able to deal with it. And so this doesn't work. And just putting on the left-hand side doesn't work either. So we're kind of stuck and we didn't know how to do it. And okay, my interpretation sort of what happened then at the time is that now one invokes actually a posteriori quite a natural trick, which is, I mean, people in PDE theory have known for 100 years, which is called freezing of coefficient. So I've just fixed some base point Z0. Now I'm just going to kind of freeze the coefficient of that V here near that point. So I just subtract the value of that V in this point. And now near that base point here, this is going to be small, and I'm going to write that term on the left-hand side of the equation. Okay, that's all I've done. And again, anybody who has ever seen the proof of, say, Schauder estimates for non-constant coefficient operators knows this trick in a sense, right? So that's what you do. And sort of now from this, you see, now perhaps if we harvest the smallness of this point, this thing here near that 0, then perhaps we get something better than before, just locally near that point Z0. Okay, so that's sort of the basic idea, and then from that you could kind of guess that it's perhaps plausible to say that the field phi, if you look at the variables y, which are close enough to that base point, then they should look like this first term that we had subtracted, and then this v that we have at the base point, and then extra terms, this comes from here, and then an extra term that comes from here. Okay, so this is how you guess this expansion that was then used later on. And now this was really nice because that now, I mean, this is now the basic ansatz. So we're going to solve this equation in some space of model distribution, and the model distribution are objects that have this structure. So they're locally well described by this expansion. And this also makes the analysis now tractable, because it separates sort of what one has to do. One has to construct this model, so these funny stochastic terms that I have here, this pi. And this can be done with one set of techniques that in principle is around. So we use moment estimates, Feynman diagrams, and also the renormalization happens here. So that's sort of the probability part of the construction. And then once we are kind of happy with all these objects, then we can do analysis. So we treat the remainder. And here we use a completely different set of tools. And I want to just single out kind of regularity estimates. So Schauder theory in particular, the celebrated reconstruction is, this is what happens here. And so this was then has been really now been the basis of this massive theory of regularity structures. And again, these 4 papers kind of are the theory now, the jargon. So if you want, this gives you a solution theory of now all semilinear subcritical SPDEs. And they're really based on these ideas. There's really now a huge zoo of interesting equations that people have to look at. And so, I mean, this is this phi-4 kind of equation that I had already been speaking. That's what I've been illustrating so far on the slide. But then there's the KPZ equation that we've already seen. And then there is, okay, this looks more fancy, geometric stochastic heat equation. So people have looked at this. This is the equation that describes the canonical motion of a string on a manifold. And then here, more recently, the stochastic Young-Mills flow, which again Martin has worked on in the last few years and got results. Yeah, I put the 3 here. So this is also a paper on the 2D case, but there's also the 3D Young-Mills flow where these dynamics have been constructed. Okay, and now so what is the thing that one actually now gets? So let's go back just a bit more hands-on. So how does this really, what is the result that one gets now for this phi-4 equation? So the way it works is one first has to regularize, and this regularization really has the same, if you want, has to play the same role as passing to the lattice before on the level of the measure. So it's in a sense the same thing. Here we convolve this at some scale epsilon, but think of it as a lattice regularization. And then you put these epsilon dependent counter terms. Before we had them in the quadratic form for a quadratic term in the measure. And now here we put them as a linear term in the equation with exactly the same type of counter terms. And then we remove the regularization. And the theorem that Martin proved in his first paper exactly for this equation was that there exists a random time such that on this, for the short time, then indeed these phi epsilon converge to a non-trivial limit phi, which one then calls the solution of this phi-4 equation. So that's nice. So now this was kind of, I've taken this talk now as an excuse to speak a little bit about Martin's contribution, but let me perhaps at this point just take a break and go back now to the original part of the story, which was this Katz-Ising model. So the result on Katz-Ising is in a sense the same. So we now look at the Katz-Ising model on a discrete torus, and we're going to choose the parameters in exactly the way that I had already calculated on the previous slide. And of course, we do this only in dimension 1, 2, and 3, because in 4 dimensions, it doesn't work. And now the interesting thing is we're going to choose this temperature here, this beta temperature, exactly like we wanted. So we had this, well, 1 was this critical temperature in the mean field case. And now we're going to put corrections. So this, we were allowed already this alpha times A, a constant, but we're going to actually put here the C gamma, and the C gamma is exactly the same. I think I haven't defined it on this slide, sorry. So I should really say that, I mean, the C gamma is exactly the renormalization constant that we have, that we had in the we have seen in the limiting equation. And the statement goes, this is a statement on dynamics. So we assume that we have convergence of initial datum and a suitable topology. And then indeed, these Katz-Ising things rescaled in the correct way do converge to the solution of this 5-4 SPDE. And I mean, I should just say, so the one-dimensional case is by now classical. So this is actually even older than this survey paper that I had discussed at the beginning. So this was done in the 90s, also by this group around Presutti in the 90s. And again, I mean, so in the 90s, they could do, of course, this calculation, and it worked in arbitrary dimension, but they were sort of stuck with the limiting theory. And then the two-dimensional result was proved well by Jean-Christophe Morat and myself a couple of years ago. And the three-dimensional result is going to be on the archive in a few weeks. So I'm saying this for a while, but it's going to be in the archive very soon. And this now really reuses completely this technique of regularity structures. Yeah, I should perhaps say one more thing here. So I should stress this a little bit. So do I have chalk here? I mean, one interesting point here I find is of course, the renormalization appears, I mean, which if you're not used to this may seem a bit odd that you want to subtract infinite constants from an equation in order to get a limit. So here I should say kind of the first order that of course is quite natural because it actually appears just as a different choice of this critical temperature. And I should also mention that actually on the level of the particle system, this is a pretty small correction to 1. Because even if the C gamma is a negative power of gamma, it gets overwhelmed by this huge positive power of gamma over up here. So this is perhaps similar to something that people who are familiar with renormalization group analysis or so know already for many years, that kind of if you're on macroscopic scales, do small perturbations, they propagate on larger scales to become infinite constants. So it's really an instance of that, I mean, it's really a pretty harmless gamma to some positive power correction to 1 that you have to do here. It's certainly not infinite. It's pretty reasonable size on the scale. Okay. So, I mean, I'm not going to give you a proof or anything. I just want to kind of tell you, so how do we prove this is, of course, we just mimic Martin's analysis on the level of the particle system. And just as we do in the, as I told you in the continuum, you have these 2 steps, this construction of the model and the construction of, and then understanding of the remainder. And for us, the most serious work is the analysis of this approximate model. So again, we kind of mimic this expansion that we had seen in the limit, and we kind of do the same thing on the level of the particle system. And here we had to, I mean, tweak a bit of the existing techniques because we work with some noise term which naturally has jumps, and it's so here we had to work a little bit. And then, I mean, the analysis part, the second part, is kind of not so bad because we can use techniques that Martin has kindly provided us and put it on the shelf, so we can just pick it up. I should also perhaps give a little bit of context. So, I mean, again, connections to between 5-4 and Ising type models have been discussed in the literature for a really long time. And perhaps I should mention here this paper from the 70s that is very well known by Simon and Griffith, where also in 5-4 model, a 2-dimensional 5-4 model is constructed as a limit from an Ising type model. The limit constructed there is a little bit different. So they do a sort of 2-scale limit where they have a funny lattice where around each point they have sort of a mean field, and then they pass to the limit of this mean field first, and then after to the continuum limit. But the point of these papers was a bit different from ours. So here the point was really to use this approximation to pass with some correlation inequalities that hold for Ising-type models and pass and use this procedure to show that they also hold for these fields. Then perhaps more recent, I should say that in the 2-dimensional case, actually this has been also generalized, and you can do the same thing for general 2 to the n models. And this has been done again a couple of years ago, in particular, I mean, by Hao Shen and myself, and then later by Martin's PhD student Massimo Berti. And one interesting point also that Massimo and Martin did a couple of years ago is they, I mean, the result that I stated on the previous slide is a conditional convergence result. It says, assuming that the initial data converges, then the Markov process converges. So in a sense, it's a convergence of Markov semigroups, if you want. But how do you know that the initial data converges? Because, and the most natural initial datum would, of course, be the equilibrium. You just start the Glauber, I mean, you start this dynamics in their invariant measure. And then it doesn't follow from our result immediately that these invariant measures also converge. And in a sense, there's some compactness which is missing. And in the 2-dimensional case, this gap was filled in this paper by Martin and Massimo. And in 3 dimensions, well, we still have to do it. It's not yet done. So I mean, that's sort of what I wanted to say. I want to perhaps just kind of ask an interesting question, perhaps technical in this case. I mean, okay, let me just say that. I mean, proving conversion of particle systems using regularity structures is actually hard work, because one has to, I mean, these models, especially when the equations are more complicated, this model can consist of a lot of terms. And then each term splits into several trees, and one really has to bound quite a number of terms. And I mean, even though, of course, this has been now made pretty systematic. I mean, the theory of regularity structures is amazing in its generality, but I would still say that it's kind of a pretty hard thing to do. For the KPZ equation, I mean, okay, for the KPZ equation, of course, there was the result in the 90s that didn't use regularity structures because they could work, there was a workaround, which I don't want to stress so much. But now there's actually this really beautiful kind of a line of works started by Gonçalves and Jara, and then later Gubinelli and his collaborators. And they have now a pretty good understanding of weak solutions of the KPZ equation. So especially they have uniqueness of in a sense, a much weaker form of solution than what is provided by the theory of regularity structures. And this has been very useful in proving convergence results for interacting particle systems, because but I mean, you have to check much less for the limit. You just get tightness pretty cheaply, and then you're done. So there's actually a whole string of papers that now prove that the KPZ equation is the limit of interacting particle systems. But this relies on a very specific feature of the KPZ equation, in particular, that you have an explicit Gaussian invariant measure. And sort of the question that I would like to put out there, I mean, is there something similar for other SPDEs? So can you find a weaker characterization for something in order to not make us work so much, and when we want to look at these kind of limits? Okay, so this is, I'm already kind of coming to the end, so I want to just summarize what I've told you. So there are these special situations have been known in literature for a long time, where you have nonlinear fluctuations and they arise in interacting particle system in specific scales. And the classical example that people already knew about for long was the KPZ equation and WASEP. And here I discussed here the convergence of Katz-Ising to 5 to the 4. And sort of one of the things I want to stress is that in order to get these SPDEs as a limit, you have to change the model as you zoom out. And I mean, Martin has given us the tools to actually describe these limits, and that's the theory of regularity structures. And I mean, what we did in our paper is that we use this discretized version of the theory of regularity structures to indeed establish rigorously these scaling results. So that's all I wanted to say, and just congratulate Martin once more on winning the prize. So yeah, That's it.